Morning students. Today we are going to see about the strength of material unit 1, tension, compression and shear. First of all, we will go through the basic information about the strength of material. Strength of material is a subject which deals with the different forms of material in the different nature by material, by applying the load, and many different aspects has been dealt in the strength of material subject. So strength of material subject which incorporates various parameters of stress, strain, load behavior, shear behavior, compressive strength behavior, and bending moment behavior, bending stress behavior. So n number of concept has been incorporated into a subject in order to obtain the relationship of any material irrespective to the composition of the material. It may be a homogeneous material or it may be a non-homogeneous material. Depends upon the situation, we can able to justify the possibilities, possible forms, and different identification what we can able to require from this material. So these are the possible informations we can able to acquire from the subject. So in that subject, we will go through the unit 1, which comprises of tension, compression, and shear. So it will be a basic introduction about the strength of materials. In this unit, we will go through the how we will apply the tensile load, and how will you apply the compressive load, and how will you apply the shear load on your object. By applying the load on object, what is the inference we going to obtain from the applying load? We will apply the load in 3 different natures of tension, compression, and shear. So these are the possible formations of load we can able to incorporate it in the member. After incorporation of this load, the material tends to deformation due to its after crossing its elasticity limit, the material will has been deformed into an another modification of shape. So by incorporation of load at different levels, different nature, we can able to expect the material to be deformed at regularized one, or it may be irregularized one. So with the help of the input, we can able to expect the output in the different forms by deformations. So by giving a input of load, we will expect the deformation of an object. So this will be the sequence of work. We will go through one by one sequence of work. First, initially the tension. The tension word deals with the main thing of applying the load in the tension manner, which is nothing but the image explains the tension nature of load. We will pull out the load of an by applying the pull out load on the object. We will apply the load as a tension load. So the tension load will be of any magnitude by the nature of the force will be towards, that is, which is leaving away from the object will be represented as a tensile force. The tensile force will be represented as a noun format as a tension. So the tension which implies us that the applying load will be away from the object. We're going to pull down the load at different ends. So this will be the nature of the load. Next, we will go through the compressive load. Compressive load will be a nature of load. The word itself implies us that we're going to apply the load in compression manner. Compression manner is which is nothing but we're going to apply the load on inward. The load will be applied on either side by inward nature of the member, inward nature to the member. So by applying the compressive load, we will expect the material going to deform in a manner of compression nature, because some material can able to tolerate the compressive load, but some materials will not be able to tolerate the compressive load. For example, the concrete is good in compression, so the concrete can able to carry maximum compressive load to a extend up to a yield level. so they can able to carry beyond the yield level and to the up to ultimate level. But in nature of steel member, you can't able to expect, because steel is good in tension, but the steel is very much weaker in compressive nature, so the material will not take compressive load as much of tensile load, so which indicates that if the material will gets vary, the nature of load will also will be vary, depends upon the material. We has to be very clear that what is the load we going to apply, and what is the nature of material that going to incorporate or that going to accept that load. So from this relationship only we can able to justify the nature of load to the member. So similarly, another one format of load is that shear load. Shear load will be applied to the member in the nature of tangential to the surface of the member. So by applying the surface load to the member, certain deformation will occur to the object. So the best example is that if you're having an eraser, if you're going to rub the eraser by zigzag manner, the surface of the eraser has been deformed, because it has been sharp edge has been turned out into a rounded edges, so which implies us that the rubber can't be able to tolerate the shear load which we has been applied on the surface. So the surface has been get deformed into a sharp edged eraser, has been transformed into a rounded edged eraser, so which is from this, so the each material can able to accept certain nature of load, and a few materials can't able to accept another format of load. So we has to be very clear that what are the nature of load good for material, what are the nature of load that is irrelevant to the material. So these are the qualities of the load we has to be predicted initially for each and every materials. So that is the main source of this subject. It will be helpful for the civil engineering aspect of point of view, as well as it has been beneficial to the mechanical engineering materials, because we both deals with directly deals the properties of the materials. So with the help of that we can able to modify the material as per our requirement. So these are the data we has to be initially predicted. With the help of this data we can able to create, or we can able to convert the material for our requirement. So the subject has been applied in the this nature of conversion from different forms of load to different forms of materials. So we'll go through one by one. First thing is that rigid body. Rigid body is nothing but the object which is which will not occur any deformation by applying the load. So it is an imaginary object, because in the world if you are applying the load up to elastic limit for any material, the material will not show any deformation or change in the structure, but by interior as well as exterior. So we can't able to visualize any cracks, or we can't able to visualize any deformation among the surface of the member. So that type of member will be a rigid body. That is, applied load will be directly proportional to the stress is directly proportional to the strain up to elastic limit. The rigid body will have, that is, stress is directly proportional to strain to the elastic limit. By applying the load, it will not at any situation, it will not cross the elastic limit, always will be on the elastic limit. So that will be a highly impossible imaginary object. We can't able to predict that object. So next we will move on to the deformable bodies. Deformable bodies is nothing but by visually you can able to see the object. All the materials will be deformable materials, because in the world all the materials will be a deformable bodies. If you are applying the load, the material will not show any deformation up to its elastic limit. After crossing the elastic limit, we can able to see the deformation in any forms. For example, if you are applying the heat to the steel rod up to elastic limit, it will be a gray color. It will not show any variation. After certain crossing the elastic limit, the material has been converted into a pinkish nature, as well as the rod has been will not be at a erected nature. It has been converted into a deflected form. So which indicates that by crossing the limit, the material has been behaving into another one format of nature. As per the Newton's third law of motion, every object has an equal and opposite reaction. So within that limit, it will not show any deformation or will not show any changes on the exterior surface. After crossing the desired limit, it will show certain deformations on the object. So next will be that in order to obtain the deformation, how much deformation has been applied to the material, so that can be easily identified with the help of strain formula, as well as how much the material has been incorporating the resisting force, that will also be calculated with the help of stress formula. Stress is nothing but force by area, that is applied internally resisting force per unit area. The load which the material can able to carry with respect to that area. So that will be represented in the form of stress. Stress is represented by an SI. In the SI system, it is represented by a symbol sigma. Sigma equal to load by area. Load, which is nothing but applied load. Applied load, it may be on kilonewton in the format of Newton, or it may be in the format of kilonewton, and any hierarchy of newtons of load. So that will be the nature of applied load divided by the respective area the load were applied on the surface. So that is mm square. The area will be measured in terms of mm square. If the object is at a rectangular manner, that will be represented as into the area will be length into breadth. If it is a square member, will be A into A, or else it may be a circular member. The area has been calculated by a formula pi by 4 d square, or else some other formation of load, that is load has been applied in any natures and any format of load. It may be a compressive load, or it may be a tensile load, or it may be a shear load. By applying the load, the material will incorporate it to nature of stresses. So the stress is nothing but load by area. Stress is represented as a unit of Newton per mm square. So these are the data. By applying the nature of load, we will expect that type of stresses on the material. If you are going to applying the tensile load on a member, we can able to expect that tensile stress which is going to incorporated in a material. Similarly, if you are applying a compressive load, we will expect the compressive load from the object. Similarly, if you are applying a shear load, we will calculate the shear stress for a material. So these are the different format of stresses. So next we will move on to the strain category. Strain is nothing but the internal deformation which has been occurred to the original deformation, original nature of the member, which is the formula indicates that strain is nothing but change in dimension to the original dimension. If you are looking forward for a length, that is strain along the length direction is nothing but change in length by original length. If you going to find out the nature of strain along the thickness of the member, that is change in thickness divided by original thickness. If you're going to predict the breadth of the member, strain along the breadth direction, change in breadth by original breadth. So by applying and by what is the result we want to occurred along the material. So based on the different aspect of materials, different aspects of requirement, we will obtain the stress and strain. So stress is nothing but load by area, strain is nothing but changing dimension by original dimension. If you are finding the value along the length direction, change in length by original length. So depends upon our requirement, we can able to predict that values. So Next, we will move on to the types. Types, as we discussed earlier, what type of load we going to apply in the material, that type of stress we will predict from the material. If you are applying a tensile load, we will expect tensile stress. If you are applying a compressive stress, we going to compressive load, we will expect compressive stress. If you are applying a shear load on a member, we will definitely predict the stress will be a shear stress. So the same variation has been obtained for the strain. If you are applying a tensile nature of load to a material, we will predict the tensile strain. If you applying the compressive strain to a member, compressive load to a member, the definitely the output of the strain will be a compressive strain. If you are applying a shear load, that load will be shear strain. So the next will be Hooke's law. Hooke's law is nothing but the material will behave without any variation. The stress is directly proportional to strain within the elastic. Up to elastic limit, the material will not introduce any deformation on surface as well as externally as well as internally. So that up to that limit, the material will behave as a elastic material. After applying the load, the material will has been deformed into a continuation of material. By applying the nature of load beyond the elastic limit, the material has been transformed into elastic limit to plastic limit. After reaches from elastic limit to plastic limit, the material will not regains its original shape. Up to that elastic limit, the material, after removing the load, the material will return to its original shape. What is the So this will be the variation that we can able to predict it. So similarly, if we are applying the load beyond the elastic limit, the material will not regain its original shape, and that material will not come to its original shape and dimensions as at the initial stage. So these are the similarities between the elastic limit and beyond the elastic limit. So up to elastic limit, the stress is directly proportional to strain. So which indicate the Hooke's is a scientist which has been identified that up to elastic limit, stress is directly proportional to strain. So after that, the variation has been getting deformed. So with this relationship, it is a linear variation by an angle of 45 degree. Up to that, the material will share its original properties to the stress as well as strain in the directly in the nature of proportionality level. So this will be the stress strain curve will be a sigma, and here it will be a strain. By within the limit, we can able to expect that within the elastic limit, we can able to predict the variation will be a linear manner. After beyond the elastic limit, the variation will be behave entirely at a different nature. So up to the elastic limit, we can able to predict that the variation will be a linear variation. So the linear variation is very much good for a material because the applied load has been transformed into strain. So will not the material will behave long lastingly into an elastical nature. So that elastical nature will extend the life of the material to a greater extent. So the service life of the material will be keep on increasing. So this law has been indicated by a scientist, which is for his representation, it is will be represented as a Hooke's law. Hooke's law, which in order to remove the proportionality, that is stress is directly proportional to strain. Stress is directly proportional to strain. In order to remove the strain, that is we are in order to remove the proportionality constant, we are introducing the constant of proportionality will be capital E. Capital E is nothing but Young's modulus. Young's modulus equal to stress by strain. Young's modulus equal to stress by strain. With the help of this we know that Young's modulus equal to stress by strain, and it will be an indicated by an symbol capital E, and will have an another format of nature of name as a modulus of elasticity. The E will have the two nature of representation. One will be Young's modulus and another will be modulus of elasticity. So the elasticity word indicates that up to that level the material will absorb and it will react, and it will not uh, it will not implies us, or it will not incorporate any nature of effect to the material. So by then by the identical relationship we has been come arrive a formula, that is Young's modulus equal to stress by strain. That the stress has been represented as a load by area, strain has been represented by a formula change in length by original length. In order to, by making a simplification, we will obtain that change in length, that is delta L equal to PL by AE. So the PL by AE is nothing but with the help of this formula we can able to calculate the deformation for a member by applying the any load, as well as it may be like the length will get varies, the area will get varies, as well as the Young's modulus, the material properties will also will get varies. By incorporating all the data into an, we can able to expect the output of deformation by an formula delta L equal to PL by AE. So next we will move on to the another category of sector of theory, factor of safety. Factor of safety is an value that is acceptable in order to increase the service life of the structure. So factor of safety as per the Indian standards IS codal recommendation, factor of safety is acceptable for all the materials in order to increase the service life of the material. So we will add factor of safety for all the material performance, because at unfortunate reasons the material may be cross the ultimate as load. So if the material reaches its ultimate load, the material definitely will tendence to failure nature. So accidents may be happen for any human being, or it may be any living organisms. So in order to safeguard the nature of any living organism, so the Indian standard has been incorporating the another one additional parameter for the structure, factor of safety. Factor of safety is nothing but ultimate stress by permissible stress. So with the help of this relationship, or ultimate load by factor of permissible, ultimate load by workable load, so with the help of that by the relationship we can able to calculate the factor of safety. So the factor of safety is an important parameter. That parameter will help us to extend the life of the structure to at any unfortunate situations. So that is the most important conversions of factor of safety. Factor of safety has been identified by the formula ultimate stress by permissible stress. Next we will move on to the most important and prominent conversion. So by incorporating the conversions, the strength of material is a problematic paper. So the problematic paper, the conversions and the numerical values are most important. We have to be very clear that how much value will be occurred for any sort of questions. So in order to make it as a very calculatively clear answer, we are converting the formulation into as a procedural manner. So in order to convert this value, we are going to calculate the conversion step by step. First will be 1 kPa will be a representation, that the full format of representation is 1 kilopascal. So 1 kilopascal, which is nothing but 1 into kilo has been transformed into 1 into 10 power 3 Pascal. Pascal has been transformed into Pascal will be transformed into a conversion of unit as a Newton per mm square. So Newton per mm square will be converted into Newton per meter square will be, that is 1 Pascal equal to Newton per meter square. In order to make it as a more simplification, Newton per meter square will be converted into Newton per mm square. So for that we will make a transformation 1 meter equal to 1 meter equal to 10 power 3, 1 meter equal to 10 power 3 mm, 10 power 3 mm, 1 meter equal to 10 power 3 mm. So meter square it will be 10 power 6 mm. So by multiplying the 10 power 6 in order to numerator, it has been 1 kilopascal equal to 1 into 10 power minus 3 Newton per mm square. So this will be the easiest conversion. Next will be 1 megapascal. 1 megapascal is nothing but 1 mega will be represented as a 10 power 6. 1 into 10 power 6 Pascal. We know that Pascal has been replaced by an SI system as a Newton per meter square. So Newton per meter square, that is, in order to make it as a simplification, we will incorporate the meter square into mm square. So 1 into 10 power 6 into Newton divided by mm square has, that is meter square has been converted into mm square by multiplying the value as a 1 into 10 power 6 mm square. So the 10 power 6, 10 power 6 gets cancelled. 10 power 6, 10 power 6 gets cancelled. Finally, we are obtaining the 1 megapascal equal to 1 Newton per mm square. So this will be the most important conversions that will be used at any format of nature of sums at any situations as per the dependency. So this will be the important conversions. Next, we will move on to the another category as a 1 gigapascal. 1 gigapascal equal to 1 into giga will be represented as a 10 power 9. So 1 into 10 power 9 Pascal. So 1 into 10 power 9 new Pascal will be converted as a Newton per meter square. So 1 into 10 power 9 into whole of n divided by 10 power 6, that is will be transformed into 1 into 10 power 3 Newton per mm square. So this will be the most important conversions. So next will be that next, after by making the respective conversions, we will move on to the deformation of sums. That is, by incorporating the different format of values, we will go through the nature of elongations for a different material by incorporating the formulas. So next we will go through the stresses for a varying material for different varying cross sections. So the stress in a bar for a different materials has been calculated. That is, we are taking the 3 different format of sizes of materials, A1, A2, A3 will be a varying size member. Similarly, by we are taking the different length of material as a L1, L2, L3. So these are the different materials, that is, these are the different sizes of materials will be uniformly jointed together into a single material. At the exterior ends, we are applying the uniformly varying, that is uniformly load along the center of the member by a load of P. So next will be in order to obtain the total elongation, we know that elongation will be represented by a symbol delta L. The delta L for a single material will be PL by AE. So delta L equal to PL by AE. The total elongation delta L for for the different variation of size of materials, delta L equal to PL by AE. That is, for a first member, that will be P divided by E into whole of L1 by A1 plus second material will be L2 by A2. Similarly, for the third material will be L3 by A3. So by adding different material, different sizes, you can able to add additional parameters by adding the length by area formula. So these are the basic variations we can able to carry out for any size of materials by varying. If the material has been varied by length, or it may be material will be varied by its area value, or the member may be get varied by its load at different nature of segments. The material may be get varied by the composition. It may be a steel, or it may be a copper. Another one material may be aluminum. So if the material elongate, that is Young's modulus will may also will get vary, may also will varies. So if the material properties also varies, the Young's modulus value will also vary. So by applying the all variations in order in a single formula, that will be delta L equal to P by E into whole of L1 by A1 plus L2 by A2 plus L3 by A3. So by a single formula, we can able to expect how much total elongation will be occurred in a material. So this formula is most important, and as well as it will be most helpful in order to obtain the elongation by varying the length, or it may be area, or it may be a load, or it may be a Young's modulus. By varying any nature of parameters, we can able to predict, and we can able to exactly calculate the total elongation of a material. So these are the topics we has been gone through in the unit 1. So we will discuss the another unit by upcoming days. Thank you.